Okay, so the next topic is pressure. Now, pressure is basically defined as force per unit area. Um, it's often the case that we use, pressure when dealing with liquids and gases, and generally we talk about stresses when we're dealing with solids. Okay. Now, when you have an enclosed volume like this, you're going to find that the pressure is the same in all directions. Okay. When you have a gas inside that chamber, or inside this enclosed volume, I should say. Okay. Um, so here's like the formal definition of it. It's a limited delta F over delta A, where this is force and this is cross-sectional area, as delta A goes to zero. Okay. Now, typically in this class, we're going to be dealing with uniform pressure. Okay. So along any surface um, of this enclosed volume, we can actually determine the force. Okay. So a lot of times what we'll be doing is looking at, a piston. What's the force acting, pushing out from the piston, or the force acting externally to it. Now, in this case, when we look at problems such as this, what we'll find is whatever the force here, this is an equilibrium situation here. So we have whatever force is acting due to the gas pushing out on the piston surface is going to be the same as the external force pushing in, at least when we're dealing with a piston at rest. Okay, that's what happens. So our formula can be then just simplified to the external force is equal to whatever pressure on the internally times the surface area of this piston, or the cross-sectional area, if you want to think of it that way. All right. The next part is just here's just units, different units. One Pascal, a kilopascal, and some conversions down here, unit conversions. Okay. Next thing we'll look at is an example. So a lot of examples here to take a look at. Okay, so the first example, what we have is a hydraulic cylinder with a 7.5 centimeter diameter. And we're looking to see how much, what the pressure inside of the cylinder is in order to create 6,000 newtons of force on the rod. Okay. Neglecting outside pressure, any atmospheric pressure. The other thing it looks like we're neglecting here is the mass or the weight of the piston itself, piston rod combination. Okay. So the problem just basically becomes, it's force, whatever force pressing down. This is another, like an equilibrium condition, a equilibrium problem. So whatever force is acting up is essentially going to be the same as the force acting down. Okay, so the force is equal to the pressure times the cross-sectional area. And what we're looking for is pressure here, so we can rearrange the equation. So it just simply becomes whatever force, the 6,000 newtons, is going to be the same forces due to the pressure acting on this area of the cylinder in the upward direction. So all you really need to do is make sure you have the correct units. You convert this over to meters, come up with an area of meters squared, and then you can actually go and just substitute in the 6,000 newtons divided by the cross-sectional area of a circle, and that gives you your end result. And that's essentially it. So it's a very basic problem, a good starting point. Okay, looking at the next problem. Okay, so the next problem essentially is the same thing, except now you're using USCS units. Okay, so you follow the same process here. Okay, so the next thing I'm going to look at is a manometer. And a manometer is just a device used to measure pressure and indicate, what that is. Okay. Okay. So when we look at manometer when we're doing the analysis, the thing to keep in mind is that uh, the pressure is the same at any 2 point, at any elevation in that liquid. So when you're at point B, it's the same in this case. In this particular problem, it's the same as A. Okay, so keep that in mind as we go through this. Okay, the author starts a solution. Um, in this case, is by taking a look at what's happening at B, at point B. Okay, so we can do this as looking at it as a force. Since it's in equilibrium, if we think about whatever force is pushing down at point A, it's got to be the same thing as what's pushing up. Okay, so what we're find is what's pushing up at A, and not to be confused with like point A and and cross-sectional area. The pressure at B times the cross-sectional area of this column is essentially going to be equal to whatever force due to the atmosphere pressing down times the cross-sectional area, and the mass of this column times gravitational acceleration pressing down here. Okay, and that's going to equal whatever's pressing up. So break it up into two parts of the equation. We have whatever force is pushing up at point B and what's pushing down at point B. So this is due to the atmospheric pressure, and this is due to the essentially the weight of the column of this liquid. Okay, so if we just break this down into a volume equation, so volume is H times A times the density, so this replaces mass essentially in this equation, times gravitational acceleration gives you the force pressing down. Okay, so we consider that to be an equilibrium. All right, so whatever's going to be on the left hand side is going to equal whatever's on the right hand. The left hand side of the equation will be this, and this will be whatever's on the right hand side of the equation. So the second part is to think about, as I previously stated, is that the pressure at B is equal to the pressure at A. Okay. And this really follows from this, the equilibrium condition here also, where the cross-sectional area at A, at B is the same as a cross-sectional area at A. Okay, so in that case, we have cross-sectional area A and A just get canceled out of this, canceled out. All right, so we have just pressure PB equal to PA. So we can rewrite this as just BO, which is just our atmospheric pressure times a change in pressure, which in this case is just due to, the density times gravity times H, because we're pulling out the cross-sectional area of this. This is just the pressure with the cross-sectional area removed, which is just from this equation. Okay. And if we place the delta P on the other by itself in the equation, we have gauge pressure. So gauge pressure is just going to be equal to whatever P pressure we're measuring minus, in our case, the initial pressure or atmospheric pressure. It's just going to be equal to the density times gravity times whatever the height of the column is. Okay? And that is basically it for this one. Okay, the next device to look at is a barometer. And barometer is just used to measure atmospheric pressure. Okay, for the barometer problem, one of the things that's required here is that we have a vacuum inside of the tube, okay? And, or a perfect vacuum, should say, right? It's a perfect vacuum. And we're basically the pressure, the atmospheric pressure here is resulting in this column being held up at a certain height, okay? And we use the same idea as previously. What we had is that if we think about it in terms of like the difference in pressure, let's say from here to the top of this column, could be represented by the atmospheric pressure minus whatever the pressure is at the top, okay? And we also have an equilibrium problem. So we're saying essentially the force at any point here, whatever's acting up, or at any surface, is the same as whatever's acting down, since it's an equilibrium condition. Okay, so we take that delta P, whatever the difference is in pressure, delta P pressure, times the cross-sectional area, gives us that force, essentially, that's acting down, which is essentially, of course, in this equilibrium condition, it's the force that's acting up. Now, since we're assuming a perfect vacuum here, we can say, or approximately perfect vacuum, we could say that the force pushing down essentially is just the mass times gravitational acceleration of this column. Okay? And of course, we can rewrite this as, density times cross-sectional area of the column times its height times gravitational acceleration. Okay? So if we take this equation here, basically atmosphere minus p top times cross-sectional area is equal to this density times cross-sectional area times that height of that column times gravitational acceleration, and we divide out the cross-sectional area, we end up with this form. So delta P times A, and we divide, like I said, divide out A on both sides. What we have here is then, we could approximate this. So P top is essentially 0 plus delta P is equal to the atmospheric pressure, which is essentially the density times gravitational acceleration times the height, h of 0. Okay, that's that. Okay, so the next problem, we're just looking at the difference between, or the pressure difference due to a column of water versus a column of air. And in this case, all you're doing is, we have for pressure, a change in pressure, from, let's say, the top here down to the bottom, would be just the density times gravitational acceleration times its height. In both cases, we have a 10-meter column of air or water. And here is the density of water. It's about 1,000 times that of air. Okay. So what this really is, the point here is just talking about is that in general, you can actually, when you're using a manometer, you can generally neglect, most cases you can neglect the pressure, atmospheric pressure from your measurement. Okay. That's all this was. Let's just show you that. Okay. Continuing on. So here just shows you the same previous example, except you're using USCS units. And 30-foot, we have a 30-foot column of water. That's the only difference. So we'll continue on. Take a look at that example. Okay. So this just shows where manometers and barometers are used. So barometer is used from absolute 0, with a reference point. So you're measuring from absolute 0. Both manometers and barometers are referenced relative to the atmospheric pressure. And when you're using a manometer, you could either measure, ordinary pressure or ordinary pressure gauge or ordinary vacuum. And the difference you'll notice is just, you're either going to have a positive H value or a column that's higher for the output if it's used as an ordinary pressure gauge. And if it's under vacuum, then what you'll see is that from the point you're measuring, the height, the column will actually be down lower than what on the output. Okay, and that's essentially the difference. Okay, in this case, we'll define the difference between static and dynamic pressure. For the most part, at least for now, we're going to look at static pressure. Okay, and the basic idea is, if it's stationary, or fluid that's stationary has static pressure, and if it has velocity um, or flow, if you want to think about it, it's flowing, then it has dynamic pressure. So in general, a system, you could talk about the total pressure as both these two added together. Okay. So here's some examples where we see that, floating objects where whatever displacement essentially equals to the mass of whatever the object, like a boat. Okay. All right. Static pressure also. So it doesn't matter what the shape is. It's only given as some point P or pressure below the surface. Okay. So it doesn't make any difference what you have in here. Right. Same thing, a swimmer or submarine. Okay. Something that's naturally buoyant. Great. And if you're dealing with something like speedboat or water ski, you have to think about both static and dynamic pressure part. Okay. So just some couple of basic definitions here. All right. Nothing on that slide. Okay. Here's an example of static pressure and buoyancy force. Okay, so we're going to look at an example of a small submarine going down to a depth of 2,000 meters, where compressed air in some tanks is used to blow air out of the blow water out of the ballast tank, and then with this, the air displaces the water that's in the tank, and since the air has a lot less mass for that same volume, the submarine will rise. Okay. Now, the first part of the question is that how much air pressure do you charge the tanks at? And with the idea is that it needs to be 100% higher than the water pressure. Okay. Second part is after pushing 0.5 meters cubed of water out, how large a force does this create, buoyancy force, to push the submarine back toward the surface? Okay, so the first part of this is thinking about the water pressure at that point at 2,000 meters. You have the top pressure, which is, whatever pressure is pushing down due to the atmosphere, plus the pressure due to the depth or essentially the column of water on top of the submarine. Okay. So for this, what we notice is from the equation, this is from previously what we had. If you're talking about the pressure at a depth, it's just the density times gravitational acceleration times whatever height or depth it's down in the water or in the fluid or liquid in this case. So first thing is we need to get is the density from a table. It's about 1,000 kilograms per meters cubed. This case, an approximation of pure water for salt water. Okay. So over on the left here is just the atmospheric pressure in kilopascals. And then you just go through density, gravitational acceleration times the depth. And in this case, you perform a calculation, and it's 19,662 kilopascals. Since it's pressure is 100% higher than what's needed, it's basically just 2 times the water pressure is what we'll need in the tanks. So times 2 times that result gives us 39.3 megapascals. Okay. Now to determine the actual force acting up, in this case, will be essentially, you can think about it, it's the mass that was removed from the tank. Okay. And in this case, it's just going to be the density times whatever volume times the gravitational acceleration. Okay, gives us that result. So here is the force, since that's the change from our equilibrium condition of what was actually pushed out, is 4,890 newtons. Okay, so that's pretty much it for that problem. Okay, pressure, nothing on this slide. Okay. Here's some examples of manometers and barometers. Okay. And one thing to pay attention here is this one is a little different. This actually measured static pressure plus the dynamic pressure. Okay. So it's a little bit different. This is actually used for both. Okay. if it's configured in this fashion. Okay, continuing on. Now we're going to get into energy and temperature. Okay, we're going to look at energy and temperature. Energy is defined as basically capacity to do work, and the temperature is really just a measure of the kinetic energy of the molecules in this system. All right. We'll look at both at the macro scale and the micro scale. At the macro scale, we can define some internal energy, kinetic energy, and potential energy. So the total energy would be all those three combined. Kinetic energy is just being the energy of motion. Okay, so it's a half m times the velocity squared. And the potential energy is just like its horizontal position, vertical position, times the mass times the gravity. So it's just essentially whatever weight is associated with times its position. Okay, so one of the things we can do when we measure or think about internal energy, we have a lowercase u, which could be thought of as, internal energy per unit mass, and then times mass would give you your energy, total internal energy. Okay, so we could break this up, the internal energy, into three separate parts, and the first part would be the basically intermolecular forces between molecules. Then we have any kind of translational kinetic energy associated with it. And then the last one would be due to the internal structure of the internal atomic structure of a molecule. Okay? Which you could even break that down into potential, rotational, vibration, and the energy of the atoms. Okay? And each mode of energy possesses 1/2 kT of energy in average, and K is the Boltzmann's constant. All right, so we'll use that later on in the class. And we have essentially, these are the different scales of temperature. We have the Celsius, Kelvin. Typically, this is the in the SI system, and this is in the USCS system, Fahrenheit and Rankine. Right, and here it gives you a chart the equivalent temperatures for the different systems, Celsius versus Fahrenheit. And here's formulas you can use to convert between each of them, and some of the common points of measure where we have phase changes. Okay, so we'll look at some of those more on Chapter 2 and Chapter 5. Okay. Continuing on, so here's some devices you can use to measure temperature. Thermocouples, thermistors, changing of resistance, of course digital thermometer, analog thermometer, thermocouples with display, and thermistors, and this one has some insulation on. So just some physical devices used to measure temperature. And that's about it for this chapter, Chapter 1.